October 15, 1943, North American Aviation Factory in Inglewood, California. The Automair carried the constant hum of Merlin engines being tested as workers hurried across the sprawling aircraft assembly floor, their footsteps echoing against polished concrete. Inside Hangar 7, Chief Engineer Raymond Mitchell stared at performance reports that should have been celebrating triumph, but instead documented frustration. The engineers believed their P-51 Mustang was perfect, its laminar flow-wing design revolutionary, its Packard-built Merlin engine providing 1,290 horsepower of raw power. They had no idea that a night shift janitor would soon prove them spectacularly wrong. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What unfolded over the next 6 months would transform not just aircraft performance, but challenge everything the aviation industry thought they knew about aerodynamics, proving that sometimes the most profound discoveries come from the most unexpected sources. Raymond Mitchell had spent 14 years designing aircraft, earning his engineering degree from Caltech in 1929, just months before the stock market crash. His methodical approach to problem-solving had earned him respect throughout North American aviation, where he'd contributed to the design of the T-6 Texan trainer and the B-25 Mitchell bomber. But the Mustang represented his masterpiece, a fighter aircraft that combined British aviation requirements with American industrial might. The performance data spread across his desk told a familiar story of incremental improvement. Test pilot Robert Chilton's latest reports showed the P-51 achieving maximum speeds of 437 miles per hour at 25,000 feet altitude, with dive speeds reaching 505 miles per hour before compressibility effects began degrading control response. These numbers represented significant achievements, particularly when compared to the P-40 Warhawk's maximum speed of 360 miles per hour, yet Mitchell sensed untapped potential within the airframe. Corporate pressure intensified daily. North American aviation had committed to delivering 500 aircraft per month to the Army Air Forces, while simultaneously competing against Republic Aviation's P-47 Thunderbolt and Lockheed's P-38 Lightning for lucrative contracts. Every mile per hour of additional speed could translate into millions of dollars in future orders, not to mention potentially saving countless pilot lives in combat situations. 3 floors below Mitchell's office, Frank Kowalski pushed his maintenance cart through the factory's maze of corridors, his worn work boots squeaking against freshly mopped linoleum. At 57 years old, Frank had worked janitorial positions for nearly 2 decades, supporting his family through the Great Depression by accepting whatever honest work presented itself. His thick Polish accent and elementary education often caused supervisors to underestimate his intelligence, but Frank possessed something many engineers lacked: curiosity about how things actually worked. Frank had emigrated from Krakow in 1924, carrying dreams of American prosperity and bringing skills learned in his father's furniture workshop. Though language barriers prevented him from pursuing technical education, Frank's hands understood materials in ways that textbooks couldn't teach. He could feel when wood grain ran properly for strength, recognize quality metal by its sound when struck, and detect subtle variations in surface texture that indicated underlying problems. The night shift suited Frank perfectly. Between midnight and 8 in the morning, the factory transformed from chaotic production environment into peaceful workspace where he could perform his duties without constant interruption. Management appreciated his reliability and attention to detail, particularly his ability to maintain the pristine conditions required for aircraft assembly. Dust particles or surface contamination could compromise delicate instruments or interfere with precise measurements, making janitorial work more critical than most people realized. During his rounds, Frank developed intimate familiarity with every section of the facility. He knew which machinery leaked oil consistently, requiring extra attention, and which areas accumulated metal shavings that could damage equipment if not removed promptly. His route included Hangar 7, where completed Mustang airframes received final inspection before test flights, and Frank often paused to admire the aircraft's sleek lines and polished aluminum surfaces. The Mustang's laminar flow wing fascinated Frank particularly. Engineers had explained to visiting dignitaries that this revolutionary design maintained smooth airflow across the wing surface by carefully controlling surface shape and smoothness, reducing drag significantly compared to conventional wing designs. Frank listened to these presentations while emptying trash cans nearby, gradually understanding that surface smoothness directly affected aircraft performance in ways similar to how proper wood finishing affected furniture appearance and durability. On the evening of October 21st, Frank encountered an unusual situation while cleaning Hangar 7. A Mustang prototype, tail number 44-25940, sat positioned for morning inspection, its aluminum skin reflecting overhead lighting in patterns that revealed subtle surface irregularities. Frank's trained eye detected areas where manufacturing processes had left microscopic tool marks and slight roughness that, while within acceptable tolerances, created a surface texture resembling fine sandpaper. Frank remembered discussions about surface smoothness affecting performance and decided to experiment with techniques from his furniture finishing background. He retrieved a can of high-quality floor wax from his supply closet, a product containing carnauba wax and fine polishing compounds designed to create mirror-smooth finishes on linoleum and hardwood surfaces. If smooth surfaces improved airflow, Frank reasoned, perhaps this wax could enhance the aircraft's performance in ways similar to how proper finishing improved furniture quality. Working methodically through the night, Frank applied thin, even coats of wax to the Mustang's wing surfaces, using circular motions learned from decades of furniture work. The wax filled microscopic surface irregularities while creating an incredibly smooth finish that seemed to amplify the aluminum's natural reflectivity. Frank polished each section until achieving mirror-like smoothness, then moved systematically across the entire airframe, treating fuselage surfaces, control surfaces, and even the propeller spinner. By dawn, the aircraft's appearance had transformed dramatically. Instead of typical industrial aluminum finish, the Mustang now gleamed like a carefully maintained automobile, its surfaces reflecting hangar lights with startling clarity. Frank felt satisfaction similar to completing a particularly challenging furniture project, though he worried about potential consequences if supervisors discovered his unauthorized modification. Chief Engineer Mitchell arrived for work at 7:30 that morning, following his normal routine of reviewing overnight production reports while drinking coffee from his standard ceramic mug. His assistant, Technical Sergeant William Hayes, intercepted him in the corridor with unusual excitement, explaining that something extraordinary had occurred with prototype 44-25940 during the night. Hayes led Mitchell to Hangar 7, where the transformed aircraft waited under inspection lights. Mitchell's engineering background provided no framework for understanding what he observed. The Mustang's surface finish exceeded anything he'd encountered in 14 years of aircraft development, resembling precision optics more than conventional manufacturing. He ran his fingers across wing surfaces, feeling smoothness that seemed impossible to achieve through normal production methods. The finish quality surpassed even hand-polished racing aircraft, which typically required weeks of specialized labor to achieve similar results. Test pilot Robert Chilton arrived for his scheduled evaluation flight at 9 o'clock, immediately noticing the aircraft's unusual appearance. Chilton had accumulated over 3,000 flight hours in various military aircraft, including extensive experience with P-51 development testing, and he'd never encountered such dramatic surface modification. His pre-flight inspection revealed no obvious problems, though the mirror-like finish made detailed examination more challenging due to reflected light. Chilton's background included barnstorming experience from the 1930s, when pilots competed in air races requiring every possible performance advantage. He understood how small aerodynamic improvements could produce significant speed increases, particularly at high air speeds where drag forces increased exponentially. If this surface modification actually reduced drag, the performance implications could prove substantial. The morning test flight began with standard procedures: engine warm-up, taxi tests, and normal takeoff from North American Aviation's private airfield. Chilton established climb attitude and power settings identical to previous evaluation flights, intending to maintain consistent test conditions for accurate performance comparison. Initial climb rate seemed normal, though engine parameters indicated slightly reduced power requirements for maintaining specified airspeeds. At 10,000 feet altitude, Chilton began performance evaluations using standardized test protocols. Level flight speed measurements showed immediate improvements. The aircraft achieved 452 miles per hour at maximum continuous power settings, representing 15 miles per hour increase over previous best performance. More dramatically, dive speed tests revealed maximum velocities approaching 545 miles per hour before encountering compressibility effects, nearly 40 miles per hour faster than standard configuration. Chilton's radio transmissions to ground control reflected growing amazement as test results exceeded expectations dramatically. His pilot training emphasized objective reporting, but the magnitude of performance improvement challenged professional composure. Control response felt more precise throughout the speed envelope, while engine cooling improved noticeably due to enhanced airflow efficiency across the aircraft's surfaces. Back in Hangar 7, Mitchell monitored radio communications while attempting to understand possible explanations for the observed performance improvements. Aerodynamic theory suggested that surface smoothness affected boundary layer behavior, but the magnitude of improvement seemed impossible according to conventional calculations. Standard laminar flow wing design already incorporated smooth surface requirements, making additional gains seem theoretically limited. Frank continued his normal janitorial duties that morning, cleaning offices and maintaining facilities while listening to excited discussions among engineers and supervisors. He understood enough technical vocabulary to realize that his surface treatment had produced significant results, though he remained uncertain about potential consequences. His immigrant background included healthy respect for authority figures and concern about exceeding assigned responsibilities. When Mitchell's team began investigating possible causes for the performance improvement, Frank's supervisor, Maintenance Chief Arthur Goldman, suggested questioning night shift personnel about any unusual activities. Goldman had worked with Frank for 7 years, recognizing his reliability and attention to detail, but also understanding that Frank occasionally took initiative beyond standard procedures when he believed improvements were possible. Goldman found Frank organizing supplies in the maintenance storage area, his usual practice during mid-morning break periods. Frank's English had improved significantly during his 19 years in America, though he still spoke carefully when discussing technical subjects with supervisors. Goldman's questioning revealed Frank's surface treatment experiment, along with his reasoning based on furniture finishing experience and observed discussions about aerodynamic smoothness. Mitchell's initial reaction combined professional skepticism with growing excitement about potential implications. His engineering background emphasized systematic testing and controlled variables, making Frank's empirical approach seem unscientific despite its apparent effectiveness. However, the magnitude of performance improvement demanded serious investigation regardless of its unconventional source. The revelation that a janitor had achieved aerodynamic improvements beyond engineering team capabilities initially embarrassed Mitchell's pride, but his intellectual honesty forced acknowledgement of results over methodology. Frank's furniture finishing background provided practical understanding of surface preparation techniques that aerospace engineering hadn't yet incorporated systematically. Traditional aircraft manufacturing emphasized structural integrity and dimensional accuracy, while accepting surface finish as secondary consideration. Over the following weeks, Mitchell's engineering team conducted detailed analysis of Frank's surface treatment, measuring finish quality with precision instruments and documenting exact procedures used to achieve the improvement. Surface roughness measurements revealed that Frank's waxing technique had reduced average surface irregularities by 67% compared to standard manufacturing finish, creating conditions more favorable to laminar flow maintenance across wing surfaces. The wax itself proved crucial to understanding the improvement mechanism. Frank's floor wax contained microscopic particles that filled surface irregularities, while providing durable, smooth finish capable of withstanding flight conditions. Chemical analysis revealed ingredients including carnauba wax, fine silica particles, and polymer compounds that created surface properties superior to conventional aircraft finishes for maintaining smooth airflow. Industrial chemist Dr. Margaret Stevenson joined Mitchell's team to investigate surface treatment possibilities, bringing expertise from automotive finish development, where smooth surfaces affected both appearance and performance. Stevenson's background included research into boundary layer behavior over curved surfaces, providing theoretical framework for understanding Frank's empirical discovery. Stevenson's laboratory analysis confirmed that Frank's treatment had achieved surface smoothness approaching optical quality while maintaining durability characteristics suitable for aircraft operation. The wax formulation created microscopic surface structure that actually enhanced laminar flow maintenance compared to perfectly smooth theoretical surfaces, suggesting that optimal aerodynamic finish required specific surface properties rather than simple smoothness. Production implementation of Frank's technique required significant modification of existing manufacturing procedures. Traditional aircraft finishing emphasized corrosion protection and durability over surface smoothness, using primers and paints that actually increased surface roughness compared to bare aluminum. Frank's approach suggested that specialized finishing techniques could provide both protection and aerodynamic enhancement simultaneously. Quality control manager James Patterson initially resisted implementing finishing procedures developed by maintenance personnel, expressing concerns about production consistency and worker training requirements. Patterson's 22 years in aircraft manufacturing emphasized systematic procedures and measurable standards, making Frank's intuitive approach seem unreliable for large-scale production. However, subsequent testing confirmed that trained workers could achieve similar results using Frank's techniques, provided they received proper instruction in surface preparation and application methods. Frank became an unlikely instructor, working with production supervisors to develop standardized procedures that captured his empirical knowledge while ensuring consistent results across multiple aircraft. The transformation of Frank's role from janitor to technical consultant highlighted broader organizational issues about recognizing expertise, regardless of formal credentials or job titles. His practical understanding of materials and finishing techniques proved more valuable for solving specific problems than theoretical knowledge without hands-on experience. Military Procurement Officer Colonel David Harrison visited North American Aviation in December 1943 to evaluate production capabilities and performance specifications for expanded P-51 orders. Harrison's background included flight testing experience with various aircraft types, providing practical understanding of performance characteristics that affected combat effectiveness. Harrison's test flight in the improved Mustang produced enthusiastic reports that reached Army Air Force's headquarters within days. The 40-mile-per-hour speed increase translated into significant tactical advantages, including improved climbing performance, extended operational range due to reduced drag, and enhanced pilot survivability through superior escape speed capabilities. Word of the performance improvement spread throughout military aviation circles, generating interest from British Royal Air Force representatives who had originally requested North American Aviation to design the Mustang for European combat requirements. RAF test pilot squadron leader Geoffrey Pemberton arrived in January 1944 to evaluate the improved aircraft for potential British procurement. Pemberton's extensive combat experience in European theatre provided perspective on performance improvements that affected operational effectiveness. His test reports emphasized that the speed increase enabled tactics previously impossible with standard Mustang configuration, including high-speed reconnaissance missions and bomber escort duties at extended ranges. Manufacturing implementation accelerated rapidly as military orders increased based on improved performance specifications. North American Aviation invested in specialized equipment and worker training to implement Frank's finishing techniques across entire production line, treating surface preparation with importance previously reserved for structural assembly and engine installation. Frank's promotion to surface finishing supervisor represented unprecedented recognition for maintenance personnel contributions to aircraft development. His salary increased from $42 per week to $78 per week, enabling financial security his family hadn't experienced since emigrating from Poland nearly 20 years earlier. The broader implications of Frank's discovery extended beyond single aircraft type improvements. Other manufacturers began investigating surface finishing techniques for various aircraft designs, leading to industry-wide recognition that aerodynamic performance could be enhanced through manufacturing methods previously considered cosmetic rather than functional. Competitor aircraft manufacturers initially dismissed reports about wax-based performance improvements as corporate propaganda or measurement errors. Republic aviation engineers insisted that surface finish couldn't significantly affect their P-47 Thunderbolt's performance, given its radial engine configuration and different aerodynamic design philosophy. However, independent testing by military evaluation teams confirmed North American Aviation's claims, forcing industry-wide reconsideration of surface treatment importance. By mid-1944, virtually every major aircraft manufacturer had initiated research programs investigating optimal finishing techniques for aerodynamic enhancement. Academic institutions became involved as engineering schools recognized that practical manufacturing knowledge possessed by skilled workers often exceeded theoretical understanding taught in formal curricula. Frank received invitations to speak at technical conferences, describing his techniques to audiences of engineers and scientists who initially struggled to comprehend how furniture finishing experience applied to advanced aerodynamics. The California Institute of Technology's Aerodynamics Department initiated formal research into surface treatment effects on boundary layer behavior, using Frank's discovery as starting point for systematic investigation of optimal surface properties for various flight conditions. Professor Harold Thompson's research team found that Frank's intuitive approach had achieved results that required sophisticated theoretical analysis to explain properly. International recognition followed as Allied nations implemented similar finishing techniques on their aircraft production lines. British manufacturers adapted Frank's methods for Spitfire and Hurricane production, while Soviet engineers incorporated surface treatment knowledge into their fighter aircraft manufacturing. Despite limited technical communication between Allied nations, Frank's personal transformation reflected broader American ideals about opportunity and recognition based on contribution rather than formal credentials. His story appeared in factory newsletters and local newspapers, inspiring other immigrant workers to contribute ideas and innovations based on their diverse backgrounds and experiences. The impact on military aviation proved substantial throughout the remainder of the conflict. Mustangs equipped with improved surface finish achieved superior performance in combat conditions, contributing to Allied air superiority in European and Pacific theaters. Pilot survival rates improved measurably due to enhanced aircraft performance characteristics that provided crucial advantages during critical situations. Post-conflict analysis revealed that Frank's surface treatment innovation had influenced aircraft development trajectory in ways extending far beyond immediate performance improvements. The recognition that manufacturing techniques directly affected aerodynamic performance encouraged integration of production and design teams, improving communication between theoretical engineers and practical manufacturing specialists. Frank's legacy continued influencing aircraft development through subsequent decades, as jet-powered aircraft presented new challenges requiring sophisticated understanding of surface finish effects on high-speed aerodynamics. His empirical approach inspired continued investigation into manufacturing techniques that enhanced performance while maintaining production efficiency and cost-effectiveness. The furniture finishing techniques that Frank adapted for aircraft use found applications in numerous other industries where surface properties affected performance characteristics. Automotive manufacturers, marine vessel builders, and wind turbine designers adopted similar approaches to optimizing surface treatment for improved efficiency and operational effectiveness. Educational institutions modified curricula to emphasize practical experience alongside theoretical knowledge, recognizing that innovation often emerged from unexpected combinations of expertise from different fields. Frank's story became standard example in engineering programs, illustrating importance of remaining open to insights from diverse sources regardless of conventional expectations. By war's end, the P-51 Mustang, equipped with Frank's surface treatment techniques, had achieved legendary status among military aircraft, contributing significantly to Allied victory while establishing performance standards that influenced fighter aircraft design for generations. The speed improvements that began with floor wax application had evolved into sophisticated understanding of surface aerodynamics that continued advancing aviation technology. Frank returned to furniture making after the conflict, establishing a small workshop in Los Angeles where he continued applying finishing techniques developed during his aircraft experience. His reputation among local craftsmen reflected expertise that combined traditional Polish woodworking methods with advanced surface treatment knowledge gained from aerospace applications. The broader lesson of Frank's contribution extended beyond technical innovation to organizational culture and recognition of expertise regardless of formal position or educational background. North American aviation's willingness to investigate and implement suggestions from maintenance personnel demonstrated enlightened management approach that maximized human resources potential. Manufacturing efficiency improvements resulting from Frank's techniques influenced post-war industrial development as companies recognized that production innovation could provide competitive advantages comparable to design improvements. The integration of practical worker knowledge with engineering theory became standard practice in advanced manufacturing industries. Modern aircraft development continues utilizing principles that Frank's discovery helped establish, though contemporary surface treatment techniques employ advanced materials and application methods far beyond 1940s floor wax technology. The fundamental insight that manufacturing processes directly affect aerodynamic performance remains central to aircraft design and production optimization. Frank Kowalski passed away in 1978 at age 92, having witnessed his simple innovation influence aviation development for more than 3 decades. His family preserved documentation of his contributions to aircraft development, including original performance test reports and photographs of the first wax-treated Mustang that demonstrated the power of practical innovation combined with theoretical knowledge. The story illustrates how breakthrough innovations often emerge from unexpected sources when curious individuals apply knowledge from different fields to new challenges. Frank's willingness to experiment with familiar materials in unfamiliar applications demonstrates the importance of maintaining open perspectives toward problem solving, regardless of conventional approaches or established expertise. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.